To wrap up our work on apportionment, let's look at some flaws that exist in some of these apportionment methods. I know it's kind of a negative way to wrap this up, but it's the best way we can think of. So earlier on in our apportionment journey, we learned about Hamilton's and Lowndes' methods. And although those two methods do follow the quota rule, where they end up assigning either the upper quota or lower quota, standard upper quota or standard lower quota to the groups, they can result in 3 serious flaws. Whereas our other methods, our divisor methods, will not result in these 3 flaws, but they don't necessarily follow the quota rule. So there's always some kind of catch. And it's not saying that these methods will always result in these flaws, but the flaws can pop up. One of them is called the Alabama paradox. Yes, that's named for the state of Alabama. I'll mention why in a minute. Another is called the population paradox, and the third is called the new states paradox. You'll find that the names were given based on what's happening in each of these. So for the first one, the Alabama paradox, let's talk about what it is, and then let's look at an example where it happens. This paradox occurs when the total number of items increases, but somehow one of the groups loses an item. It's like you would think if the total number of items being passed out or portioned goes up, then at the very least everybody should just keep their original apportionment. But somehow a group ends up losing one item. And this was named for the state of Alabama, as I mentioned a minute ago. In 1880, they were talking about, in the U.S. House of Representatives, about going up from 299 representatives to 300. And at that time, if they did this and went up to 300, it was going to cause Alabama to lose a rep that they already had. So somebody else was going to still gain, actually, if they're going to lose a rep, that means you've got 2 others that are going to gain reps, because somebody's going to gain the extra that they're adding, and then somebody's going to gain Alabama's that they've just lost. But this is what happened. So that's named for Alabama. So let's look at our own example of what this looks like. All right, so the ever popular states A, B with letter names. We've got 100,000 population. We've got state A with 40,650. We've got state B with 38,650. State C with 10,400. And state D with 10,300. All right, and in this situation, we're going to show that this paradox arises if the number of seats increases from 99 to 100. So we're going to go through and see what the apportionment looks like with 99, and then we're going to redo the math to see what the apportionment looks like with 100. All right, so starting with 99 seats, if you have 100,000 population in this country, then we can find our standard divisor by taking 100,000 divided by 99. You're trying to see, how many people would be represented per seat. So I'll do that down here because I didn't leave myself enough room. So we're going to do 100,000 divided by 99. And we're going to get 1010.10. That's probably enough to just use that. All right, so then we can go through each state and figure out that state's standard quotas. So you take each state's population, divide by that standard divisor, and see what you end up with. So you can probably hear my calculator clicking away. I'm going to write it to 4 decimal places because remember, with this method, we're going to need to look at those decimal parts to decide how to award the leftovers. Remember, Hamilton's looks just at the decimal part, whereas Lowndes looked at that relative fractional part. We're not going to do Lowndes right now, but these same paradoxes can occur with Lowndes' method also. All right, so anyways, so standard quota, the integer part is 40, And we don't know yet what's going to happen as far as who's getting leftovers and all that stuff. Okay, so the next one, 38,650. We're going to divide that by the 1010.10. It's almost a little poetic, saying 1010.10. And I get 38.2635. So the integer part is 38. Then 10,400 divided by 1010.10. I have 10.2960. So the integer part is 10. And then 10,300 divided by 1010.10. So I get 10.1970. So the integer part is 10. All right, so if I add those up right now, remember that's 99 seats. But right now, these only add up to 98. So I do have a leftover to hand out. So remember, with this method, I look at those decimal parts. So maybe I'll use a different color. I've got a 0.2435, a 0.2635, a 0.2960, and a 0.1970. Remember, you start with whoever has the highest decimal part and give them the first leftover. In this case, there's only one leftover, so only one of them's getting an extra beyond what's already there in those integer parts. So it looks like state C has the highest decimal part, so state C gets one more. So for the Hamilton's apportionment, state A stays at 40, state B stays at 38, state C goes up from 10 to 11, and state D stays at 10. And that adds up to the 99 seats that are apportioned in this example. Okay, so we're going to do the same example over again here, but the seats are going to be 100 next time. So we're going to have to do a whole new standard divisor, new standard quotas, new integer parts, new Hamilton's apportionment. And we're going to see what happens. We're going to compare our results. So let's write out the populations again. State, let me give myself a little more space this time. Let's write state A, state B, state C, state D. Yep, so then we're using the same populations and all that. Still 100,000 total. And we had like the 40,650, etc. So we had 40,650 for state A. We had 38,650 for state B, 10,400 for state C, and 10,300 for state D. So for our standard divisor, this time we're taking 100,000 and dividing by 100. So that comes out to 1,000. So that'll be a lot easier to do our quotas. Dividing by 1,000 is nice because you just move your decimal point 3 places over. So easy. All right, so our standard quotas, if we divide 40,650 divided by 1,000, we're going to get 40.65. Just move your decimal place 3 places to the left. For state B, we're going to get 38.65. State C, we're going to get 10.40. State D, we're going to get 10.30. So we have a 40, a 38, a 10, and a 10 for our integer parts. If you add those up, you get 98. But remember, this time we have 2 seats to hand out because now we have 100 total that we're handing out. So there's 2 leftovers that got to go somewhere. So once again, we got to look at these fractional parts. You have to make an agreement ahead of time what you're going to do if 2 of them have the same fractional part and you have to just give one. But we've lucked out. We don't need to make that agreement this time because our 2 fractional parts that are the highest are both we've got 2 seats to hand out, so it works out. We don't have to come up with some agreement. So we're going to have 41, 39, because those two had, A and B had the highest fractional parts, so they bump up one each. And then C and D are going to stay the same at 10 and 10. And that now adds up to 100. So that's good. So with this additional seat, if we're going from 99 to 100, this would be your state's apportionments by Hamilton's apportionment. But let's compare. What happened here? Ooh, interesting. Hopefully I don't make you too dizzy going back and forth. State A went from 40 to 41, which, you gain a seat. You figure somebody's going to go up one. State B went up from 38 to 39. Uh-oh. Two states went up one when we only had one extra to give out. So that means somebody went down. And it looks like state C was that somebody. They went down from 11 to 10, while state D stayed the same. So only one extra seat. But two states went up one, while one state went down one. This shouldn't have happened. What should have happened was just one state should have gained that extra seat. Nobody extra should have gained a seat. Nobody should have lost a seat. So that's where this paradox is occurring with this method. And that's what was going to happen to poor little Alabama. That's all right. They seem to be holding their own in football and stuff nowadays, so I don't think they're too upset about it. But still, it can happen. So that's what you think. The kinds of things you have to look at closely when you're trying to do the apportionment math. All right, next paradox, population paradox. This paradox occurs when Group A's population grows at a faster rate than Group B's, but somehow Group A loses an item to Group B. All right, it's not saying that Group A is necessarily bigger or fast or better. It's not saying that Group B is bigger. But what it's saying is that we're looking at the rate of growth, how quickly somebody's gaining like a population. If Group A is growing at a faster rate, if anything, they should either stay the same or gain more representation because they're growing fast. But in the population paradox, even though Group A's population is growing faster than Group B's, somehow Group A loses an item to Group B. It makes no sense. Trying to think of an example. Like, all right, so say you have like a bunch of people suddenly making a mass exodus from bitter cold in Alaska to Florida. So Florida's population is growing at a certain rate, and Alaska's is not keeping the same pace. But with the population paradox, what would happen is somehow Florida would lose a seat in the House of Representatives to Alaska. It's like, why is that? I mean, Florida is the one growing at a faster rate. Makes no sense. So this happened, actually there's an example, when Virginia was growing faster than Maine in the early 1900s, but somehow Virginia lost a seat in the House to Maine. This population situation. All right, so let's look at our own example. It's not Virginia and Maine, it's just some other made-up example from a textbook I have, A Mathematical View of Our World. All right, so this time we're just going to do 3 states. We've got state A, we got state B, we got state C. Old population column, new population column. Okay, so state A had 95.55, then grew to 96.51. State B had 19.545, grew to 19.740. State C had 70,900. Grew to, and it stayed the same, 70,900. Put little commas in there so we can see those thousands. All right, so let's look at the rates of increase, the percentage increase in the population growth there. Well, State C didn't change, so there was a 0% increase there. So that one, we'll just take note that there was 0% increase, and keep an eye on it. But let's do a little bit of math to see what's happening. To get your percent increase, same idea with percent decrease. New population minus old divided by old. And then change to a percent. So like for state A, you got 9651 minus 9555, and you would divide by 9555. Okay, so let me pull out my trusty calculator here. So subtract up top, you get 96 over 9555. So, and then divide that by the 9555. And you get a decimal. This is the decimal version, but then you want to change that to a percent. So we'll go ahead and write that as 1.0047%. Okay, state B, same idea. 19,740 minus 19,545 divided by 19,545. Got 195 over 19,545. So if you do the decimal there, 0.009976976. I just wrote down whatever my calculator spit out. So percent increase is 0.99. Let's go to 4 decimal places. 9977%. Just move your decimal 2 places to the right, and that changes it to a percent. Okay, so right now state A has a greater percent increase than state B. Not by much, but it is still bigger. So we could say that state A is growing slightly faster than state B. So let's see what happens with our apportionments. Let's see what happens with old population versus new population. All right, so we have states A, B, and C. Old population, standard quota, and then we'll just go ahead and look at Hamilton's apportionment, or look at integer part and Hamilton's apportionment for that. And then we're going to do same thing with new population. We'll just compare them side by side. So new, standard quota, integer part, Hamilton's apportionment. All right, state A had an old population of 9555. B was 19,545. C was 7,900. Okay, and we're going to go with 100 seats in the legislature. So we have 100,000 people. divided by 100 seats equals 1,000 for our standard divisor. So that's what we're going to use. We're going to say 100 seats for these 100,000 people. Use that standard divisor and go through and work this out. Okay, so for the state A, if you do 9555 divided by 1,000, remember that just moves your decimal. You get 9.555. So the integer part's 9. I don't know yet what my Hamilton's apportionment's going to be because I have to see what happens with leftovers and etc. The next one's going to be 19.545. Nice and easy because we're divided by 1,000. Then 70.900. Sorry, it looks squished. So we have a 19 and a 70. Which if you add those up, 18, 8, that adds up to 98. So we have 2 seats to hand out. We have to look at those decimal parts to decide who gets them. And it looks like states A and C get those extras. Okay. So your Hamilton apportionment there ends up being 10, 19, and 71. So that's going to be important to pay attention to later. All right. Now next to that, let's look at the new populations and what happens. The new populations were 9651, which when you divide by 1,000, you're going to have a standard quota of 9.651, integer part 9. Second new population was 19,740, so you're going to have 19.74, integer part's 19. The third was still just stayed the same, 70,900, so 70.9, integer part's 70. All right, so what does that add up to? That still adds up to 98 because it's the same as earlier, but our decimal parts are different. So let's take a look at those. We have 2 to hand out this time, not going exactly the same places. We're going to hand out the extras to states B and C because 74 and 90 are bigger than 740 and 900 are bigger than 651. So states B and C will bump up 1. State A will stay the same. So the Hamilton's apportionment there is 9, 20, and 71. All right. So as expected, state C stayed the same. But state A basically lost a seat to state B. But state A lost a seat to state B. Because originally, with the old population, state A had 10 representatives. With the newer increased population, state A went down to 9 representatives. With the old population, state B had 19 representatives. With the new increased population, now has 20. State C's population stayed the same, the reps stayed the same, which you would hope. But yeah, what was our growth and our percent increase? But state A had a larger percent increase than state B. And that's where this seems unfair. Albeit small, State A's rate of growth is still greater than State B's. State A should not have lost a seat to State B. I mean, if they had both just stayed the same, that would be okay. Like if, State A had kept State A had kept 10 and State B had kept 19, nobody would have complained. But it's the fact that State A is growing faster than B, but yet lost to B. That's your population paradox. Pretty wild, isn't it? All right, one more. New states paradox. This occurs when an established group's apportionment changes after a new group has been added. Paradox was seen in 1907 when New York lost a seat in the House to Maine after the addition of Oklahoma as a state. All right, so you've got these two states sitting here minding their own business. We add a new state out west, out in the Midwest, called Oklahoma. You expect, all right, we're going to need to increase our number of representatives so that Oklahoma gets some. So they do. And Oklahoma does get extras. But somehow in the math, Oklahoma doesn't, not only does Oklahoma just get those extras we just added for them, but somehow one of New York's seats ends up in Maine. It's like, what? New York and Maine should have just been left alone, and Oklahoma should have just gotten those extra seats that just got added for their benefit because they're new. So this is called the new states paradox. It's pretty wild, isn't it? All right, let's look at an example. That's not Oklahoma, New York, and Maine, but it'll show you what happens with the numbers. Okay, let's say you have 2 states, 100 reps. And there are 100,000 people. So if that's the case, standard divisor will be the 100,000 divided by 100, which is 1,000. All right, so State A's population is 9,450. State B's population is 90,550. So standard quota, divide by 1,000 because that's your standard divisor. You're trying to see how many groups of 1,000 does each state have. So just move your decimal 3 places to the left and get 9.45. The integer part is 9. For State B of 90.55, integer part is 90. This adds up to 99. Sorry about that. So these decimal parts, we need 100 seats handed out. Looks like State B gets the extra. So the Hamilton's apportionment here is 9 for State A and 91 for State B. Okay, so no big deal so far. But now we're going to have a State C come along. States A and B are going to keep their same populations. State A is still going to have 9,450 people. Nobody's leaving to go to State C. They're staying put. They like their houses. State B has 90,550. So they were adding in a State C with 10,400. All right, so let's add 10 reps for State C. So we have 110 reps. And let's redo the math. Our standard divisor this time, instead of 100,000 people, we now have 110,400 because of State C. We'll divide that by the 110 reps. Not quite as pretty as earlier, unfortunately. So I'll pull out my calculator. So you have 1,003.6364. So that's my standard divisor. So I'm going to take each state and divide by that. So I get like 9.416 under my standard quotas here. Integer part is 9. I see IP now, I think Instant Pot. I don't know if anybody else has one of those, but anyways. All right, sorry. 90,550 divided by 1,003.6364. I have 90.22. We're going to 3 decimal places, so 90.222. So my integer part's 90. And then 10,400 divided by 1,003.6364. So 10.362. So that gives me 10 for my integer part. All right. So these add up how? These add up to 109. Short one rep. So I gotta, I like using pink. So I gotta go back and look at my decimals. 0.416, 0.222, and 0.362. State A has the highest of those. So state A gets my extra in the Hamilton apportionment. So state A goes up to 10, B stays at 90, C stays at 10. Oops. So there is my Hamilton apportionment for those 3 states. Okay. So as we expected, state C ended up with those extra 10 that were added for them. Good, that's great. But let's go back up and compare the situation for A and B before state C came along. A had 9 and B had 91. Now A has 10 and B has 90. What on earth? Why? Well, the math worked it out that way, but this just doesn't make any sense. State A and B should have just been left alone. Nobody should have messed with them. State C should have just gotten those extra 10 and been done with it. But that's an example of your new states paradox. State C received the 10 reps added for them. But somehow, again, state A lost or gained a seat, state B lost a seat. State A went up to 10, state B went down. Somehow state B lost a seat to state A. I feel like I said that wrong earlier. I don't remember now. Sorry if I did. Because B was 91, now it's 90. A was 9, now it's 10. Why did A go up? Doesn't make sense. They should have just been left alone. So there you go. So that's a mathematical example of the new states paradox. And to take a glum note and end it on a further glum note, we have Belinsky and Young's impossibility theorem. Belinsky and Young are 2 more brilliant mathematicians to add to your mathematician list. This particular theorem was proven by them in 1980. It wasn't that long ago. I mean, you really do the math, that was like 40 years ago, which to some of you was really like before you were born, but whatever. It wasn't that long ago. Okay. So this theorem basically says there is no perfect apportionment method. No method will both satisfy the quota rule and avoid paradoxes. So like in our examples that we've learned about, Hamilton and Lowndes' method follow the quota rule. You're going to get either the lower quota or upper quota. The standard lower quota or standard upper quota. But we just learned about these 3 paradoxes that could pop up in those 2 methods. And then all your others, your Webster's, Adams, those other guys that we learned about, those divisor methods, those don't necessarily follow the quota rule because you have to use that adjusted divisor. You have to do a modified divisor, modified quota. Yeah, that was having a little brain lapse. So it was I'm trying to remember. It was Jefferson, Webster, and Adams. Those three. I'm trying to remember all three names. But anyways, in their cases, you don't get these paradoxes. Yay. But since you're using that modified divide or modified quota, you don't necessarily follow the quota rule. So it's impossible. Any apportionment method you come up with, even if it's not one of these, no method is going to satisfy everything. And on the top of that, these methods tend to favor either large groups or small groups. Like we talked about this in the slides along the way, but just a quick recap. Where did it go? So let's see. You had Hamilton's method favored the larger states. Lowndes' method favored the smaller states. So that was a situation with the two quota methods. Now with divisor methods, Jefferson's favors large states. Adams favors smaller states. Webster's was pretty good about really not favoring either type, so that's great for it. So, I mean, many of them, like, it didn't really favor either type too much, but still, yeah, the whole quota rule situation. So, no perfect method. So that's Walensky and Young. And that's all I have to share with you about apportionment methods. Something to think about. We just did a census this year. Hopefully you all participated. Census is important to help us figure out our representation for that, not just the House, but also for tax purposes and other things, levying taxes and such. So local and state and national government, it's important. But apportionment is the math behind like figuring out based on that census, figuring out who gets what. And then prior to this, we talked about voting, and right now we're just had our vote. At this point in time, our president-elect is Joe Biden, so that's where we are when I'm recording this. So if you're watching this in the future, that'll give you an idea about how far back I'm doing these videos. But I already did the videos on voting methods, and so that process is kind of interesting too, because we see it in action with our government. But I guess I should end it there. Thank you for joining me, and I hope to see you again soon.